Nuclear Renaissance, Fact or Fiction? This presentation covers the U.S. portion of our Capstone project. Today's reactors are derived from designs originally developed for propelling submarines and large naval ships. They generate about 85% of the world's nuclear electricity. The USA accounts for more than 30% of worldwide nuclear generation of electricity. The U.S. nuclear industry has a capacity factor of 92.2% as of 2015. Almost all of the U.S. nuclear generating capacity comes from reactors built sometime between 1967 and 1990. There are 61 commercially operating nuclear power plants. Some of these nuclear power plants are being shut down not because they have reached the end of their useful life or even political reasons. They are closing due to economics. It's been a combination of several factors, some of which are market related. Some of these factors are sustained low natural gas prices, which are likely to continue in the future, low growth in electricity demand, federal and state mandates for renewable power, which also suppresses prices, and a lack of market understanding of how nuclear power contributes value to baseline power production. In 2015, the average generating cost for nuclear energy was about $35.50 per megawatt hour. In 2015, the costs are 2.4% less than in 2014, and almost 11% less than what was in 2012. The smaller single-unit plants ran for about $44 per megawatt hour. The larger multi-unit sites were in the $33 per megawatt hour range. Nuclear power, meanwhile, is assumed to be too expensive to build. On the other hand, nuclear power plants provide large-scale, steady baseload electricity once they're built. When looking at the actual cost of generating electricity, nuclear power is still one of the cheapest. And countries that rely heavily on nuclear power have below-average retail electricity prices. Nuclear power has stagnated in recent years. The average age of a U.S. commercial reactor is about 35 years. The oldest operating reactors are Oyster Creek and 9 Mile Point 1. Both of these reactors entered commercial service on the 1st of December in 1969. The NRC licenses U.S. commercial nuclear reactors for 40 years. Companies may also apply for 20-year extensions. 83 of today's 99 operating reactors have received extensions to 60 years. 15 others plan to apply for extensions. Utilities have been using power uprates since the 70s as a way to increase their power output. More than 7,300 megawatts of power uprates have been approved. That's the equivalent of adding 7 reactors to the grid. The NRC has 3 types of power uprates: measurement uncertainty recapture power, stretch, and extended power uprates. 3 more uprates are pending, with an additional 10 more power uprates expected by 2020, for a total of another 190 megawatts electric. There was the 30-year period in which few new reactors were built. It's expected that 4 new units will come online by 2021. They are Vogtle 3 and 4, and Summer 2 and 3. 10 large units and 12 smaller units have also been planned. There are millions and millions of neutron impacts per year on the reactor pressure vessel during operations. At some point, it begins to impact the reactor vessel materials. This is true for all the materials in a reactor, including the fuel and cladding. U.S. leadership in the field is unnatural, given the sheer age of America's reactors. Many of those reactors are already coming close to exceeding their intended operating lives. Until recently, research has just not been a priority. The Department of Energy began a program looking at long-term operations in hope of extending plant lives. Research takes time, money, facilities, and talent. In the U.S., it takes a lot of time and money. The AGR-23 experiment took close to 6 years from design to examination. You can't just pull a fuel element out of a reactor and take it to any lab for analysis. There's a lot of overhead associated with a nuclear-capable lab. The U.S. is working to develop high uranium density fuels for research reactors. This fuel is intended to enable conversion from highly enriched uranium, HEU, to low-enriched uranium, LEU. Since 2004, the Global Threat Reduction Initiative, GTRI, has converted 7 domestic research reactors. There are 2 fuel designs being developed around a uranium-molybdenum alloy fuel, a dispersion and monolithic version. Now, some of the current work in this program is the heating of compacts in a fuel accident condition simulator furnace to a peak temperature of about 1700 degrees C. Leach tests on AGR hardware to provide data on fission products released. Next generation nuclear plant and advanced gas reactor fuel development and qualification programs. AGR2 experiment irradiation and post-irradiation examinations, or PI, and AGR3 and 4 irradiation and PI. The purpose of the JFCS program is to conduct generic research and development, R&D, as well as generic non-R&D activities related to used nuclear fuel, UNF, nuclear waste management, and disposal issues. It's also to conduct R&D on advanced sustainable fuel cycle technologies. Some of the current work supporting this program is the recovery of purified uranium transuranic alloy product from the uranium electrorefining process, fission gas sampling on Futrix fuel pins, oxide reduction, or OR, testing using an oxide reduction furnace, ORF, corrosion testing of uranium silicate for fuel cycle research and development programs, Futrix pin examinations for increased burn-up potential of fast-spectrum fuels. This program supports strategies of long-lived radioactive waste transmutation in Gen 4 crit fast neutron reactors. And lastly, many new pieces of equipment, glove boxes, and facility modifications are taking place in preparation for upcoming work in this project. Some of the advanced non-light water reactor designs are sodium fast reactors, high-temperature gas reactors, lead fast reactors, and a gas fast reactor. Other points of interest in the program are targeted laboratory R&D programs, an advanced test and demonstration reactor study, and most importantly the Gateway for Accelerated Innovation in Nuclear, or GAIN, initiative. The GAIN program seeks to streamline the certification process. SMRs, or small modular reactors, are a fascinating branch of nuclear R&D. There are 4 main competitors in the U.S. SMR field. They are NuScale, a light water integral pressurized water reactor, or IPWR, utilizing natural circulation, BWXT mPower, an advanced light water integral PWR, SMR 160, a small modular reactor designed to use LEU fuel, and TerraPower, a Gen 4 traveling wave liquid sodium cooled fast reactor. The NuScale design utilizes natural circulation. The reactor and containment vessel operate inside a water-filled pool that is built below grade. The module stands 76 feet high and 15 feet wide. Up to 12 of the modules can be monitored from a single control room. The output is expected to be 50 megawatts electric per module. The module is designed to be built at a factory, then shipped to a site for deployment. The BWXT mPower reactor and steam generator are located in a single vessel located in an underground containment. The reactor uses LEU, less than 5% enrichment, as fuel and produces 100 megawatts electric. The design incorporates passive safety systems. The SMR 160 is a conventional LWR that utilizes low-enriched uranium fuel. The motors and pumps have been replaced with gravity-driven fluid flow systems. All safety-significant systems must be powered by natural circulation. The SMR 160 complex is small and would fit on a conventional soccer field. The SMR 160 is designed to be part of a distributed power system to reduce the need for power distribution lines and decrease power grid vulnerabilities. TerraPower's Traveling Wave Reactor, or TWR, is a Gen 4 liquid sodium cooled fast reactor based on existing fast reactor technologies. The design allows depleted uranium to be used as the primary fuel after the use of a small amount of enriched uranium at initial startup. The TWR is supposed to be able to operate for an extended period of time without refuel. Some of the current materials research taking place now is advanced radiation-tolerant materials, such as the analysis of titanium silicon carbide. More specifically, ceramic material titanium silicon carbide max phase shows excellent radiation damage tolerance after irradiation. There's the characterization of irradiated X750 alloy to test for crack growth rates, fracture toughness, and tensile strength. And thermal analysis was conducted on new fuel alloys designed to mitigate the corrosion of cladding material by rare earth fission products at high burnup rates. The rate at which fuel and cladding react, fuel-cladding chemical interaction, or FCCI, during irradiation is critical to fuel performance. FCCI thins the cladding wall, shortening the fuel life. Current research is on the characterization of FCCI in transuranic fuel. Determination of phases formed in the fuel and fuel-cladding chemical interaction to understand the fuel and cladding interfaces. Accident-tolerant U3-Si2 fuel characterization, eutectic formation experiments of trigger elements to determine fuel operating limits, trigger fuel performance under loss of coolant accidents, or LOCA, uranium nitride, uranium oxide, UN/UO2 composites. UO2 has a better radiation damage resistance, and uranium molybdenum research reactor fuel development. UMO fuel increases the blister threshold temperature and provides increased operating margin. And fission gas, xenon and krypton, bubble swelling in the UMO fuel. TRISO fuel is designed to retain fission products such that each sub-millimeter particle is its own fission product containment and a traditional reactor containment building is not required. Current studies attempt to show how radioactive products would migrate through a graphite compact if a TRISO fuel particle ruptured. Microstructural evidence was identified for focused corrosion of silicon carbide by palladium in neutron-irradiated TRISO fuel. The prismatic or pebble bed aspect of the fuel design refers to the core design. The prismatic design is being considered for the next generation nuclear plant, or NGMP, project, and is known as the Very High Temperature Reactor, or VHTR. The unique feature of pebble bed reactors is the refueling capability in which the pebbles are recirculated within the core. The system allows new fuel to be inserted during operations and the spent fuel to be discharged during the life of the plant. Some of the non-power production aspects of the nuclear industry are medical, radioisotope thermoelectric generators, or RTGs, space, homeland security, research, education, regulation, and support of the U.S. Navy nuclear-powered fleet. Some medical applications of the nuclear industry are mammography, to look for and diagnose breast cancer or diseases, computerized tomography, or CT, which is a technique using X-rays and computer processing to generate two-dimensional pictures. Think a single slice of bread and a loaf of bread. Nuclear medicine, where radioactive material is administered. The radioactive substance allows doctors to determine if organs in the body are functioning. Cardiology angiogram is where contrast agent is injected and an X-ray is taken of the heart to check for function. And radiation oncology. We have several different types of that. The first is brachytherapy, where a small radioactive metal implant is put inside the body in or near a cancerous tumor. A linear accelerator, LINIAC, a device that emits high-energy X-rays and electron beams. The linear accelerator beam can be collimated so the energy is delivered to the tumor while sparing normal tissue. And a gamma stereotactic radiosurgery, or more commonly known as a gamma knife. Very high doses of radiation are delivered to very small diseased areas. RTGs are devices that convert the waste heat given off by radioactive decay into usable electrical energy. RTGs can function in hostile environmental conditions that are not conducive to generating electricity by natural means, such as solar or wind. NASA uses RTGs to power space probes. Current work on RTGs consists of a new high-temperature graphite furnace used to bake off impurities from graphite materials, vapor hydrogen peroxide, VHP, biosterilization of components, and research on multi-mission radioisotope thermoelectric generators, or MMRTGs. The only flight of a fission power source, or FPS, was the 1965 launch of the SNAP-10A reactor on the Snapshot mission. Larger and more powerful sources of power were required for longer and more complex space missions. Nuclear power is being considered for lunar and Mars missions. NASA is examining small reactors designed for use on other planets. Manned flights to Mars and asteroids will require specialized shielding for the occupants from cosmic radiation and perhaps from RTGs or nuclear power sources. It's estimated that an astronaut would receive 0.66 sievert on the 253-day trip to Mars. Mars has no global magnetic field. Once on Mars, shielding will be required too. Many opportunities abound in the nuclear field for homeland security. Most opportunities revolve around detection and protection of radioactive material. Additional areas include nuclear power plants, non-power nuclear reactors used for research, testing, and training, manufacturers of nuclear reactors or components, radioactive materials used primarily in medical, industrial, and academic settings, nuclear fuel cycle facilities, decommissioned nuclear power reactors, and transportation, storage, and disposal of nuclear and radioactive waste. One can see from this paper that an enormous amount of research is being done in the fields of nuclear reactor design, fuels, material, and resolution to current issues. The research itself has many opportunities in the nuclear industries. Many support positions are required to perform research. Individuals will be required to educate the next generation of researchers, engineers, and support staff. The graying of the nuclear industry will put many demands on the present educational staff, and programs must be ramped up to meet the upcoming wave of retirements in the nuclear industry. We are experiencing the start of a moderate construction phase starting to ramp up after a 30-year hiatus. The U.S. seems to be lagging behind other areas of the world in actual construction of nuclear power plants. I believe that we are at the start of a large uptick in the nuclear industry in the U.S. Construction will increase. In addition, there's far more to the nuclear industry than nuclear power generation.